afternoon session will actually feature much more about it. So we will trace back the material, hopefully, to the initial stages and see where we end up. So the first talk of today is actually on chemical habitability, and it will be given by Johanna Teske from Carnegie Institute in the US, shared with Sebastiaan Krijt from the University of Exeter. Please.
All right, good afternoon. Congratulations on making it to the last session of the conference. Welcome back from lunch. Thanks very much to the conference organizers again for a wonderfully engaging and interesting conference. It's my great honor and pleasure to give this overview talk for our chapter about chemical habitability with Sebastiaan and on behalf of our amazing team. I think our author list exemplifies the cross-disciplinary sort of hearty yet vegan soup of expertise that's needed to piece together the past and present and future of habitability. I learned a lot as an astronomer who studies planets around other stars in writing this chapter, and we really won't have time to cover all of it today, so I hope you'll enjoy reading it in detail. But just setting the stage, much of what makes Earth the precious pale blue dot that we all know and love can be attributed to the Schnapp's elements, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Clearly, these elements are of central importance to Earth's biosphere. They really are the biosphere at an elemental level, and they also play a fundamental role in abiotic dynamics of the modern Earth, from processes at the top of our atmosphere all the way down to our planet's core. And so a planet being Earth-like in a broad definition that's sort of used in occurrence rate studies, for example, really still allows a lot of room for non-Earth-like conditions on and inside the planet. And we think that these differences will really be rooted in a planet's divergent history and how Schnapp's are gained and lost during that time. So these factors were our motivation for our chapter on chemical habitability, which we distinguish from sort of the classical habitable zone, largely externally constrained definition. We say that chemical habitability includes the supply of these Schnapp's elements, and that they're going to be accessible for prebiotic chemistry over the lifetime of the planet, over relevant geologic timescales. All life on Earth requires a solvent, water, energy like from the sun, and these bioessential elements to construct molecules and polymers with different shapes and uses. And given the abundance of these elements in our Milky Way, it can be argued that life originating elsewhere probably still makes use of them. So it's important to spend time studying and tracing them in planetary systems beyond the sun. So our aim for this chapter was really to synthesize ideas about how small, temperate, rocky planets gain and lose the Schnapp's elements during their formation, and to identify key branching points where a planet's chemical habitability could be drastically changed. This is really building on and in the context of all the work that has come since Protostars and Planets VII, which we've heard about all week, from the wonderful new ALMA observations, revolutionizing our understanding of protostellar and planetary systems, the simulations that those are informing, all the new exoplanet discoveries, and some tastes of JDUS-T observations. But despite all of these state-of-the-art observations and synthesizing them into models, it's still very challenging to make detailed characterization of terrestrial analogs outside the Earth. In fact, even finding them is challenging depending on how you define analog. And so important context is really coming from increasingly sophisticated views of how planets form, tracing those processes that affect chemical habitability, starting from planets at home, and then looking at how those processes could change on other worlds around other stars. So starting at home, the Earth provides a very important constraint on how planets might attain this chemical habitability, because in principle we can actually do the accounting of the Schnapp's content and fluxes through directly or indirect methods. on the Earth. And so there are two standout aspects of modern Earth that really depend intimately on these elements. The first is our geodynamic mode of plate tectonics, where the surface is moving as rigid plates that are destroyed at subduction zone and form at mid-ocean ridges. This process connects the deepest parts of our mantle to our atmosphere and biosphere and allows those SHOPS elements to be removed from the surface by sequestration and then restored to the atmosphere and biosphere during degassing. And so this process also really depends on the presence of water to decrease fault strength and allow those blocks of crust to slide past each other. The carbon cycle is this other key process. Earth is the only rocky planet in the solar system with a functioning carbon cycle, and this regulates the temperature of the planet, as we heard yesterday. This also depends on abundant liquid to enable silicate weathering that sequesters the carbon dioxide in mineral form. So it could be that these two things really help define the habitability of a planet. I think that's still TBD, and I'll come back to that point. The Sean elements in early Earth were also probably key to creating habitable conditions during the fainter young sun period, when the radiation from the sun wouldn't have been efficient to maintain liquid water at the surface. In our chapter, we have a really nice set of tables that outline the different SHNOPS budgets on the planet, including levels of uncertainty. I don't have time to go over them here, so I'm going to just flash them really fast, and I sort of blurred out the numbers so you can't try to read them. Oh, sure. Okay, sorry, you can hear me better. So just wanted to give evidence that they are there and you should use them. Just as an example, tracing carbon in the Earth, it's mostly in the core because it's an iron-loving element at high pressures at which metal silicate segregation took place on the Earth. This sequestered much of Earth's carbon away to not make it available for bioprocessing. Really the efficacy of the silicate weathering process is evidenced in the low atmospheric content of carbon, but there is a large crustal carbon pool. So that's sort of how carbon is divided in our planet, very roughly, but definitely check out the tables for a much more detailed background. Again, all the SHOPS elements exist in major stores in the core of Earth, pointing towards core mantle segregation as really a key process that influences the surface or bioavailability of these elements. So there are plenty of SHNOPS in the core overall to support our biosphere, but making them available is important and key. So I talked about maybe what processes are really required for habitability. Maybe there are alternate routes of formation that can lead to decreased or increased fluxes of these elements. So on stagnant lid planets, of which modern Venus is likely an example, the thick lithosphere can only exchange with the interior by sort of blobbing off at the bottom, and volcanic decasting from the interior is suppressed. On Earth, in addition to the presence of water sustaining this plate tectonic regime and vice versa, Earth's magnetic field is also enabled by plate tectonic's effective extraction of heat from the planet's interior. And the magnetic field then helps preserve the planet's surface liquid water. On Venus, it lacks these mechanisms and so doesn't host an internally generated magnetic field. So that's kind of the bottom corner. What if a planet was overly lucky in SHNOPS elements? The higher surface pressure from a thick water ocean might reduce a planet's ability to have magmatism. That would replenish the surface and drive those stabilizing feedback cycles. It could also result in too much dilution and not be good for creating closed environments where chemistry can happen. Carbon's impact on the climate very much depends on how it's speciated in the atmosphere and in the mantle, both of which depend on how oxidizing those reservoirs are. So the mineral form of carbon really has a dramatic impact on its release into the environment during magmatism, with reduced forms retaining carbon in the interior more effectively than oxidized forms. But carbon isn't just passively responding to the redox state, it also is setting how oxidizing planetary reservoirs are. And so the C-to ratio of the planet really, of the planetary building blocks, really also is key towards controlling the mineralogy, the geodynamics, the climate, and thus the habitability. A high to CO ratio, one might think it's good for the origin of life, and maybe more reduced conditions, prebiotic chemistry wouldn't have to compete as much with oxygen. That will readily react with reduced compounds, which life is built out of. Adding nitrogen, because it's highly insoluble in magmas, that probably just adds it to the atmosphere, which would contribute more towards warming. It's a little bit less clear what sulfur, adding more sulfur or phosphorus would do, but I think studying planets like Venus, both for the stagnant Lynn regime, but also maybe a sulfur-rich regime, that's going to be an interesting pathway moving forward with missions like Da Vinci and Veritas. All right, so I talked about Earth over its lifetime and presently, but what about how it formed? When and where did these Schnapps elements come from? Just giving a quick orientation timeline. We start roughly at T0 with CAI formation. This is the oldest nebular condensates. After that, the gaseous solar nebula dispersed about 4 to 5 million years afterwards, at which time Mars was mostly fully formed, and both Earth and Venus had large enough primordial atmospheres of hydrogen and helium to they had those atmospheres, but those atmospheres weren't so large that they could be lost after the nebula dispersed. The most likely proto-Earth accretion scenarios, yes, there we go, are constrained from different isotope systematics and chronometers. And then we have the moon-forming impact, which is arguably the most dramatic event in the history of the Earth and the Moon, I guess, which occurred some 50 to 150 million years after the formation of the solar system, after the nebula had dispersed. Overall, based on the distribution and behavior of Schnapps in the Earth, we sort of paint this picture of Earth's formation in 4 acts and use Schnapps to track the planetesimal assembly stage, planetesimal heating by short-lived radionuclide decay, which we heard about from Steve, and that drives metamorphic volatile processing and loss, the eventual planetesimal melting and growth, and then magma ocean crystallization in sort of the last stage. So stages 2 and 3 are periods of potential significant loss of these Schnapps elements, either to space or just through the growing metallic core. In the last stage, the planet is massive enough to retain a lot of these elements, although hydrogen is still lost at this stage. And let's see. Carbon and nitrogen, also as you can see from the arrows there, are being expelled from the crystallizing magma ocean into the young atmosphere, and sulfur might be substantially lost in the lower mantle and outer core, or sequestered there. Finally, the abundance of highly siderophile elements in Earth's mantle that really should have sunk to the core during an energetic impact indicate that Earth probably collided with a population of leftover planetesimals after the giant impact in a late veneer that makes up a very small percentage of Earth's final mass. So there's a lot more nuance to that story and detailed information about each element in our chapter. But here I just wanted to highlight the importance of inner versus outer material delivery to get Schnapps to the Earth. And we heard about this in several other talks, so I won't go into too much detail. It's a little bit hard to see, but Earth is considered to be largely built from material that's isotopically similar to the enstatite chondrite meteorites, which are typically linked to asteroids in the innermost edge of the asteroid belt, and they're usually considered to be dry, although I'll come back to that. Chemically, however, there are several differences when looking in more detail. So Earth's upper mantle doesn't match enstatite chondrite magnesium to silicon ratios, and the bulk silicate Earth, carbon to nitrogen, carbon to hydrogen, and carbon to sulfur ratios differ from enstatite chondrites. And they're more similar to carbonaceous chondrite meteorites that probably are forming farther out than the asteroid belt. However, there's nuances here. So for example, if you look at the carbon to sulfur ratio, that really seems to line up, the bulk silicate earth really seems to line up with the carbonaceous chondrites. Whereas for carbon to nitrogen, maybe there's a little bit of a difference. Maybe bulk silicate earth is slightly higher. And based on some recent experimental results by Grewal et al., 2019, looking at the solubility of carbon in different sulfur, like sulfur-rich or sulfur-poor conditions versus nitrogen, which seems to not change its solubility, they proposed instead that actually this ratio can be explained by a single Mars-sized impactor, fairly volatile poor, and presumably the Earth-Moon forming impact, and that really was the source of delivery of carbon, nitrogen, and sulfur to bulk silicate Earth. So if we think Earth accreted these Schnaps elements from different reservoirs, why are there different reservoirs and how did they get into the Earth? Dynamically, it's often tied to the formation of Jupiter, kind of as a barrier between carbonaceous and non-carbonaceous type materials. And maybe during its formation, it could have scattered more carbonaceous type materials inward to account for what we, again, observe in the Earth. However, as we heard from Tim and Mickey, non-planetary origins are also possible to explain this dichotomy, and really in any context, different condensation, snow or tar lines play an important role in controlling the compositions of the building blocks and contributing to the water and carbon content on the Earth. I just wanted to highlight a couple sort of interesting updates or aspects to this picture that are particularly relevant for Schnapp. So in addition to the classical isotope dichotomy that I showed before, there's also a dichotomy in nitrogen. The nitrogen 15 to 14, ratio of bulk silicate Earth falls between these two reservoirs, suggesting again that Earth's current nitrogen reservoir was accreted from both inner and outer solar system materials. It just points towards isotopes of volatiles also being useful for discriminating between the reservoirs. Perhaps we'll hear more about that in the next talk. And one of these very interesting results actually found that enstatite chondrites are not dry, that their hydrogen and nitrogen isotopic compositions match those of Earth's mantle, shown in green here at the bottom. Enstatite chondrite-like bodies might have contributed these volatile elements to Earth's crust and mantle. You probably still need some contribution from other bodies to match the ocean and atmospheric hydrogen and isotopic compositions, but again, maybe not as much carbonaceous chondrite material is needed as previously thought. In terms of carbon, it's well established that Earth is carbon poor compared to other solar system bodies. You can see the bulk silicate Earth is extremely carbon depleted, and even accounting for what's in the core, we still have to get rid of carbon somehow. And so this could be explained by carbon loss in Earth, precursor material early on, through early sublimation within the first million years or so, when the soot line was still beyond Earth's main feeding zone at 1 AU due to disk heating by accretion or these high luminosity outbursts that we've heard of. And so this could sublimate refractory inorganic carbon in the inner disk. So that's a quick rundown of Earth, its composition and formation in the solar system. Obviously, that's a great resource. We have a lot of information, but it's just one outcome of planet formation. So we also want to trace these elements in different astronomical settings. And so this is like the very small part of the chapter I contributed to. Zooming out, these elements, the Schnaps elements, have these different nucleosynthetic origins in stars that vary in abundances and proportions as stars are born and die and move across the galaxy. Here in this movie, I'm going to show a plot of stars with abundances measured from the Apogee and Galah spectroscopic surveys. The Kepler footprint is here, as you can see, and the colors of the stars are color-coded by their metallicity, being solar or subsolar, above solar. So metallicity clearly plays an important role in planet formation. We know about the giant planet metallicity correlation, And we think this decreases at smaller planet masses and sizes, but there aren't a lot of obvious differences between stars that host planets and those that don't, besides that correlation. So I think there's been a lot of work done trying to connect host star refractory abundances to the compositions of planets. But when it comes to SHNOPS, we really need to follow them farther along in time than just the natal disk abundances and use them as a tool to learn about planet formation. So with that, I will hand it over to Sebastiaan.
Great, thank you, Johanna. Thanks for first placing us firmly back here on Earth, and then for reminding us about our place in the Milky Way and the fact that the elemental abundances vary quite a lot for different stars. So it's my this point basically. So it's my pleasure then and an honor to present to you here some ideas on how these SHNOPS elements, these life essential elements, how they behave during the planet formation process, and how they actually find their way from the ISM into these small temperate rocky worlds. So just right off the bat, there's good news and there's bad news. Okay, the good news is we now really do have this well-established, sort of unbroken chain of events, going all the way from the small molecules and dust in protoplanetary disks to either the giant planets in the top or the rocky planets on the right. I think Mihkel talked about this as well earlier in the week. I think with these new ideas of pebble accretion and planetesimal formation through the streaming instability, we really have this roadmap almost now for how to follow materials during planet formation. The bad news is that while we have the sequence, there are great uncertainties in some of the individual steps, and these are linked to sort of fundamental uncertainties in very basic disk properties, right? What is the mass in disks, the temperature, what is the nature of turbulence? This prevents us at this point from really constructing detailed forward models of all these processes together. Two more points that I wanted to highlight with this figure is that at all these scales, dynamics and mixing are very important. We heard about planet migration earlier. Planetesimals can move and scatter, as discussed earlier today in the context of the solar system. Pebbles will obviously drift across great radial distances, but even small grains can move around and bounce around because of diffusion and turbulence. So we need to worry about how these things move. And also, in this middle sort of region, we have all these objects present at the same time, potentially, right? So we have to worry about how these different size scales, these different reservoirs interact. Let's start with the raw materials, though. These elements don't enter protoplanetary disks as atoms, right? Chemistry starts very early in the dense ISM and in cold molecular clouds. We heard about it also on Tuesday morning. So based on ice abundance, ice absorption spectroscopy, mostly, you can try to do an elemental accounting of where all the individual SHNOPS elements are. And what you find here, for example, is that oxygen, carbon, nitrogen are distributed already very early between different carriers with different degrees of either volatility or non-volatility, right? So carbon, for example, is about half of it is in CO, very volatile. The other half is in refractory carbon grains or organics. And this will depend on whether this material, when inherited into the protoplanetary disk, is mostly in the gas phase or in the ice or in the solid phase. There's some open questions, of course. Right? There's some oxygen missing, some nitrogen missing. Nitrogen in particular is very interesting. Is this a highly volatile carrier like N2? Or is this something more stable, maybe ammonium salts, based on the finding of these in Comet 67P? For phosphorus and sulfur, these are we see these in atomic form in the diffuse ISM, but then they form ice species for sulfur mostly. A few % is accounted for in molecular clouds, and phosphorus we think is mostly in refractory dust, again based on comet observations of dust in comets. Some of this complexity survives when material is incorporated into protoplanetary disks. We see this by comparing here protostellar molecular abundances on the vertical axis and cometary abundances based on 67P. Yeah, so you can see this clear one-to-one line with deviations, obviously, suggesting that at least some of the protostellar abundances are directly inherited in the ices in the cold outer regions of the solar system. But this is not true. We don't think this holds for the inner solar system, right, where material is heated, sees higher temperatures, and is reset basically to atomic conditions, only to then condense out at higher temperatures. So this is illustrated very well in the context of CHNOPS by sulfur, for example. So this is adapted from a plot, thank you, of Mihkel. So sulfur is very volatile in the ISM. We see a mix of volatile and more refractory carriers in the comet-forming region, but in the terrestrial planet formation region and in chondrites, most of the sulfur is bonded to iron and in a much more refractory phase. So in the inner solar system, we think material is reset at at high temperatures. And this mix between inheritance and reset is one of the, where exactly this dividing line lies in other disks is a very important question. Class 2 disks are colder, okay, so this means the molecules are harder to see. They freeze out onto dust grains, and of the few hundred species seen in protostars, only 24 molecules or so have been identified in protoplanetary disks. Just to remind you, the way we see these is either with ALMA, we can resolve them spatially in the millimeter, right? So these are all different molecular carriers, or in the infrared, you can see them in the inner disk, but none of these observations are tracing really the midplane in the terrestrial planet formation region. The angular resolution is not good enough with ALMA, and the optical depth is too high in the inner disk. So we rely on models. I want to focus on what is really new since PP6, and I think that is this focus on pebbles, right? Pebbles, pebbles, pebbles. Pebbles are very important. Pebbles are the particles we see when we image disks in ALMA and millimeter continuum. Pebbles are the precursors of planetesimals through the streaming instability and gravitational collapse, and pebbles are the food for protoplanets growing via pebble accretion. And in these models in these modern models of planet formation, you have tens to hundreds of Earth masses worth of solids drifting radially. What does this do to your CHNOPS? Well, potentially, based on, again, on models, this is a huge opportunity, this will lead to huge changes in very important elemental abundance ratios. So carbon to hydrogen, oxygen to hydrogen, but also carbon to oxygen, as you bring in lots of water ice into the inner disk, and potentially also a lot of refractory carbon, which can then completely overwhelm any of this early depletion you have seen that Johanna also mentioned. This can be completely washed out by this inward flux of carbon from the outer disk. Those are cartoons and models. Do we actually see any of that in observations? It's an interesting question. Maybe, right? So this is for HD 163296. This is a radial profile based on ALMA and NOEMA CO and CO isotopological observations. And you see this depletion in the outer disk, so this is outside the CO snow line, and an enhancement potentially inside the CO ice line, so inside 70 AU. And this matches fairly well pebble evolution models that include sort of vertical settling of pebbles and their radial drift. And you can in fact use that then to put a number on this pebble drift flux at this specific location in this disk. You find about 15 to 60 Earth masses per million years, which is not too far off of what planet formation models need. That's the CO ice line. If the pebbles can keep drifting, at some point they will hit the water snow line, and if they can go through that, they will evaporate and potentially bring water into the inner disk. So here, every point this is looking at a larger sample of disks. Every point is a disk, and we seem to see that the chemistry in the inner disk, as traced by this Spitzer line flux ratio, responds to the size of the pebble dust disk. Yeah, so a story could be that small disks on the left are more water-rich in the inner parts because they have seen this pervasive pebble drift. But it's hard to link these line flux ratios to abundances, but this is the type of story we can try to tell. If your dust keeps drifting even further, so you cross the snow line and you cross the dust sublimation radius, you can enrich the inner disk gas now, although very close to the star, which you can see in atomic form in the infrared. And Melissa had some really nice work a few years ago showing how the depletion of refractories, but also volatiles in the inner disk, can be combined with a dust transport model to learn something about the composition of the dust and the planetesimals that are stuck further away in the disk, right? So this is the stuff you're not seeing as returning in here, and you can use it to say something about the composition of the planetesimals. Potentially, it's very exciting. You find that they are, yeah, sort of a mix of chondritic and cometary like abundances. Okay, CHNOPS are not just passengers. Okay, they influence the planetesimal formation process, we think. Ice lines have long been discussed to be preferential forms of planetesimal, or preferential sites of planetesimal formation. In fact, there are some models that can explain the entire solar system just by having 3 belts of planetesimals at the silicate, water, and CO ice line. It's curious in that context, or it's interesting, that apart from HL tau, where the substructure in dust seems to match up with sort of major ice lines, we don't really see a trend like that in, let's say, the D-sharp or other or larger surveys. So it's not so clear here. Moving on, once your planetesimals form, we think they inherit the composition of the pebbles locally because gravitational collapse is fairly gentle. Volatile loss in collisions is probably small, but large and planetesimals that form early, Tim talked about it, are expected to devolatilize and degas and lose all the volatiles as they are heated by short-lived radionuclides. So knowing where and when your planetesimals form is very important for this step because it controls their thermal evolution. Okay, pressing on. There's an ongoing debate to what extent pebble accretion versus planetesimal accretion matters in the inner solar system even. Of course, it's not either or, right? We'll have some mix of these, especially as the pebble flux is a very strong function of time, so you can imagine some process dominating early and the other process dominating late. And it's interesting then to consider the CHNOPS sort of loss and gain process associated with these. So planetesimals clearly can deliver volatiles, but it'll depend on the architecture of your system. Do you have a giant planet that's capable of bringing these things in? For pebbles, yes, these almost by definition come from much further out and can bring oxygen, carbon, we discussed it. Yes, thank you. But they may lose it on their final approach to the planet, right? So Mihkel mentioned this also briefly. If your atmosphere of your protoplanet is hot and dense enough, you can still get rid of these volatiles, ablate or sublimate the pebbles, and then mix it back to the nebula. Okay. Instabilities and migration, very important for shaping the final stages of the architectures. Don't have time to go into it, but again, inward migration can lead to very water-rich planets being present in the inner disk, even though they formed much further out. And then for late accretion, this is a very interesting point. If your resonance chain of small planets survives, you can use its stability to put constraints on the amount of late accretion. So here for TRAPPIST-1, these gray dots indicate the maximum amount of water accreted late, so after the disk has cleared, because if you stuff any more asteroids into the system, it will go unstable. And this is sort of similar to what the Earth has on the surface, but it's well below the water abundances that have been inferred by fitting mass radius diagrams. Yeah? So maybe you can still include all the water early, but there's limits to what you can do late. Okay, I'll start wrapping up, I promise. So we identify all these potential branching points that control the total amount of CHNOPS in small rocky worlds. Environment is very important. It enters in a couple of these points. I didn't really have time to discuss it here. Geophysical evolution, as Tim and Mickey described yesterday, also very important. We have to do this all together. Just to highlight 2 types of systems, and then I'll stop, that I think are very interesting in the near future. It's this question of what happens to rocky worlds in systems without giant planets, right? We have to remember that of the sun-like stars, only about 10% or so have a giant planet. Only about 10% or so of those have a cold giant planet. So what happens in these other 99% of systems? Do we really get all this extra carbon, all this extra oxygen, all these extra volatiles into the inner system? And if yes, does this really end up on your rocky planet? Do you form these water worlds? Or does it go to the gas? This is a very interesting question for placing the Earth and the solar system in context. And I think here we'll learn a lot by these sort of synergy studies that combine JWST spectra of the inner disk with ALMA, like D sharp or MAPS surveys of chemistry in the outer disk. So we saw some James Webb spectra already. This is from a different group, from Cycle 1 programs led by Klaus, Andrea, and Colette from the States. So what you see is this huge, well, first of all, it's much better than Spitzer, okay? You see all these water lines, all these hydrocarbon lines. Yes. And you can, this will be great. The second system I wanted to highlight, just in 10 seconds, is what about planets around M dwarfs? Planet formation, all the signs are saying it's just slightly off. It's slightly different around low mass stars. Disks disappear faster. There's more planets in the inner regions. Pebble accretion is way more efficient comparing snowline to snowline. And then yes, the habitable zone is closer in around low mass stars, but it's further away from where the snowline was. So this is an interesting difference also of low mass stars between low mass stars and sun-like stars. This result's very interesting, right? Mass radius diagram of planets around low mass stars inside the ice line seem to fall into these two sort of densities, either rocky and Earth-like, or these water worlds. Are we really seeing these 50 weight% water world-like planets? I don't know, but we'll find out, because all of these ones will be observed during JWST Cycle 1 programs. And with that, sorry I went a little bit over. Please ask me about future outlook, or ask about future outlook. And I'm looking forward to some carbonated volatile delivery, maybe later today. I think we've all deserved it. Thanks a lot.
Thank you. So, thank you for a wonderful talk. The floor is open to questions, so please line up behind the microphones. Yes, please. Yeah.
Satoshi Okuzumi from Tokyo Tech. So thank you for very nice talk. And you mentioned the importance of pebble drift and the transport of materials in disks. I broadly agree with that idea, but we, including me and you, we have to be careful about the efficiency of pebble drift, because the stickiness of dust particles is not very known. So we shouldn't overemphasize the high efficiency of pebble drift. It is possible that the dust particles might not be sticky and their drift might be slow, or another possibility is that if there's pressure bumps in the disks, they might stop the drift of dust particles. In that case, we cannot expect the efficient inward transport of dust particle materials. So this is just a comment.
Yeah, I completely agree. And that's why I try to focus also on these potential observational signatures of how can we use Schnop's molecules or elements that we can observe actually to pin down these fluxes. I think that's a very interesting avenue. But I completely agree. If there's substructure or if the particles are smaller for some reason, yeah, you'll see much less.
Yeah.
Yes.
We need to compare our dust evolution model with the millimeter observation of the disks.
Yeah, thanks.
Okay, thank you. We go to the next question, which is behind there.
I'm Masaru Kobayashi from University of Cologne, and I have a question on the sublimation of refractory carbon. So this is a question for non-experts, so I may have a bit confused, but where does that million year after CAI, that time scale of the million year comes from? Like, is it coming from the age of the chondrites, or is it something like depending on the model of the sublimation?
So I think this comes from the fact that you see this carbon depletion already in some of the chondrites, right? Which began to form already in the first million years.
Right.
And getting rid of it afterwards is difficult. So in the sublimation picture, you remove the carbon when the precursor particles are still very small. So you would have to do it before they are combined into these larger parent bodies. I think that's the idea. Yeah.
Okay. Thank you very much.
Okay. We have the next question here.
Huan Yuteng from Tokyo Institute of Technology. And I have two simple questions. As you know, many ongoing surveys are searching for and characterizing terrestrial planets around cool stars. So my first question, that is, could you please comment something on the difference, well, if any, of habitability of rocky planets in higher complexity and planets in lower complexity? And the second one, that is, would you comment more on what we can expect to observe these extrasolar small rocky planets with future instruments, for example, the JWST or some large on-ground-based telescope to study their habitability? Thank you.
Sure, thanks for your question. So the first one was, are you talking about sort of habitability in the context of like those compact multi-systems versus ones that are less compact?
Yes.
Yeah, so also I would ask maybe people who study the compact multis also this question, but you could think about how, I mean, just looking at the similarity in sizes and masses of the planets, that could be some constraining factor on the amount of volatiles that they're able to accrete. I had a question to Sarah yesterday about whether the densities of the planets also show similarity, and I think the answer is still TBD, but that might be interesting. Just in terms of like chemical habitability context. And then your second question was about the observability of kind of temperate rocky planets?
Well, the habitability of small rocky planets, well, with the future instruments.
Right, yeah. So I think we'll get a hint of this with JWST, looking at basically the TRAPPIST-1 planets. There's another large GEO program that's looking at rocky planets around M dwarfs in particular, so that also gets at your second question. I think basically the first level question is, do they have atmospheres at all measurable?
Yes.
And so I think in the next year or so, we'll have at least a tentative answer to that. But then something I'm excited about is kind of the next generation of large ground-based telescopes where we can not only do kind of lower resolution transit spectroscopy, but maybe start to do the higher resolution spectroscopy as well and be able to probe the atmospheres of these planets, if they have them, at different levels to get a better idea of the volatile inventory.
All right, thank you.
Yeah.
Okay, we go here to the front.
Yeah, Martin Cordner, NASA Goddard. On the subject of the origin of Earth's nitrogen, I was wondering if the devolatilization during accretion of the Earth is known to have been sort of complete, or would there have been any leftover nitrogen in the atmosphere after that?
So, hang on, let me real quick. Yeah, so on this plot on the left, what's compared here is sort of is total bulk silicate Earth, nitrogen isotopic ratios, and then compared to this NC and CC reservoir. So it's the nitrogen we still have today in the bulk silicate Earth. To get that, you have to mix these two reservoirs, and then depending on how much nitrogen you sort of just elementally you could put in the NC versus CC, you find these sort of 30 to 60%. Something like that contributions. Now that doesn't tell you anything about any of the nitrogen we've left, right? So it may well be true that the Earth accreted a larger pool of sort of more refractory nitrogen early on, which was subsequently lost, and that it's only sort of these later stages that see these 30 to 60% mixture. Yeah, that's true. Does it answer your?
Yeah, thanks.
Right, thanks.
Okay, we go back to that side, please.
Yes. Hi, I'm Margot Leemker from Leiden Observatory. So first of all, thank you for the nice talk. And I was wondering, you mentioned that in the outer disk, most of the material is inherited from the earlier phases, whereas in the inner disk, it's reset because it's much warmer. And I was wondering what your opinion is on the effect of outbursts and stellar variability on this.
Yeah, I think that's a great question. No, I agree. I think it can be very important, especially with sort of planet formation now happening. It seems earlier and earlier in our models and in our theory. We have to worry about what the temperature structure of the inner disk was early on, and whether its evolution was punctuated by these outbursts or not. So I have it here somewhere. Sorry, I'll get there. definitely, sort of in the theory part, I think we need to start including this in our dust evolution, in our chemistry dust evolution coupled models to have these outbursts. Yeah. So potentially during outbursts, I think the main thing what we'll do is you'll temporarily heat the disk, so your snow line, your water snow line, your tar line, your soot line, whatever you want to call it, will move further out. And then it's a question of whether the material that is affected by that, how much of that actually ends up in the planet building blocks, right? Or whether you lose that later. Because maybe planetesimal formation is also triggered by an outburst like that, right? As you change the dust size distribution potentially. So I think linking those, yeah, will be very interesting for sure. Yeah, thanks.
Thank you.
We have one more question behind there. Yes.
Hi, Marie-Lise Steinmeier from University of Copenhagen. I have a question about specifically fitting these volatiles to the Earth. Should we also take into account the estimates we have from the composition of Mars and try to use a model that forms both Mars and Earth at the same time? Because if I remember correctly, Mars is less depleted than Earth, so we would need to explain this depletion pattern between masses somehow.
Yeah, not my area of expertise, but I would say yes. We have such rough estimates of the properties of sibling planets and other solar systems that using the relationship between Earth and Mars and how similar or different they are in our solar system, I think could be a really powerful tool for then putting the exoplanets in context where our vision is much more blurred. But yeah, more detailed answer, I would have to defer to other experts.
Okay, next question.
Ilse Cleaves, University of Virginia. Thank you very much for the talk. So my question is, sometimes you see results about, speculation on the composition of a planet based on its mean density and then what the star is made of. Based on your analysis of exploring all the ways in which things can be shifted and changed, is this kind of exercise actually even worth doing? Can you put a broad error bar on what are the ranges of possible compositions a planet could have without knowing, anything about it in detail? What do you think?
So I can give one, and then maybe you can answer. But I was actually just reviewing this today. So these comparisons have really been made for refractory elements. So really using iron to silicon or magnesium to silicon ratios, and using that to predict kind of the core mass fraction of rocky planets. Even that process, it seems to work okay using solar abundances for solar system planets. It works for some exoplanets, but there are several cases already where we see that using, say, the stellar ratios to try to predict the core mass fraction of a planet where you have the mass and radius, those do not match. So why is that? I think it's very interesting that they would not match. And I think that's telling you something about the formation process of that planet. And so that could actually be a really powerful tool, but it also means that just the default star equals planet is probably too simplistic, at least for the refractory. I think for the volatile elements, that is definitely true. Star does not equal planet. So I don't know if you want to say anything else about that.
Yeah, no, I would agree. Maybe yes for highly refractory elements, no for volatiles. And then maybe to add that for volatiles, we see it in the inner solar system, but even taking just the variation in the inner solar system is maybe not enough, right? Because these things all formed in the inner solar system, within sort of where Jupiter was around and in one disk. We see this huge variation from disk to disk and disk evolution. So we may need to think sort of, bigger.
So I think the error bar would be large.
There's one more question there on the right.
Hi, thanks for the excellent talk. I'm Suchi Narayanan from the University of Hawaii, but now I do sulfur experiments at the CFA. So my question is naturally about sulfur. How do you think that our improvements in sulfur experiments will help with the mystery of the missing sulfur, and where do you see sulfur and phosphorus having an impact PP8 and beyond in these models?
So this is where we could have really used Mihkel, who was originally supposed to give the talk, but couldn't make it, unfortunately, in the end. Let's maybe chat afterwards. I think there's a lot to be done. I mean, so sulfur goes missing sort of early when we look at molecular clouds, and only a small fraction of it is accounted for in ICES, as Melissa McClure can now see with her ICE-ACE JWST ICE-H project. where does it go? How does it get turned into more refractory carriers in the solar system? And then what happens to that during the early evolution and sort of the geophysical evolution that Tim describes? Yeah, definitely. Let's chat.
Thanks, I'll be in touch.
And I would just also add, with JWST, we're getting access to a much wider suite of elemental or molecular abundances in the giant planet atmospheres, and sulfur species and nitrogen species are in there. Phosphorus, not so much, but we could, that's going to be another window for those elements.
Thank you.
Let me take my privilege as a chair here and provoke you even more after Ilse's question and this one. I mean, what is your opinion about taking then the isotope ratios, for example, to trace back like histories of how planets formed? I mean, this is leading up, of course, to the next chapter, but I'm just curious to get your opinion.
I mean, so far, you mean just for solar system planets? Or?
Yeah, no, I mean, we see this intriguing dichotomy, say, in the asteroids, for example, and we think it tells us something about the history and how things came together, you know, in the context of planetesimal paddle formation models, etc. But what is your view on that? Do you think we can take that as a powerful tool, or should we take it with a grain of salt?
So again, this is not my expertise, but just in writing this chapter and learning more about it, it seems like that is not a closed loop yet, that there's still a lot of, I mean, even like Tim and Mickey were talking about yesterday, ways to potentially explain these dichotomies. And so then how the cause of the dichotomy and how that then propagates through the planet formation models, I think that's actually something I'm really excited to be following more of for the next protostars and planets. I don't know if you have another answer. Okay.
So, okay. With that, let's thank our speakers again. Thank you.
All right, this is yours.